Have you ever thought about a problem you met in real life, where the problem doesn't seem to be solvable in poly time? For instance, take this example. I have 4 cars numbered 1, 2, 3, 4, and I want to sort them into 2 groups, so that the sum of the cars for each group is equal. Now, someone might tell you that if the problem, not only 1, 2, 3, 4, but also the more sophisticated cases, is proven that to be poly time, then most of the problems that are assumed to be not polynomial time must be proven as polynomial time as well. Is that true at all? The answer is yes and no. What do I mean by that? Well, let's try to uncover this question through today's main focus, NP-Completeness.
Before we directly head on to the definition of it, let's start by defining prerequisite terminology. Undecidability means that there are no algorithms for some problems, which is another topic that can discuss further, so I'll stop from here for that word. The word that we should be interested in is intractability. This means that there exists no polynomial time algorithms for some problems, where usually the majority of combinatorial problems are in this area. Then, how can we prove that there exists no polynomial algorithms? We use polynomial time reductions for checking intractability. A reduction R from the problem F1 that has input in the set X1 and output in the set Y to the problem F2 that has its input in the set X2 and output in the set Y is a simple algorithm or computable function such that it matches of input of F1 to an F2, and for all x in X1, F1x should equal F2Rx. This means that the problem F1 is through the reduction, a small subset of F2. If this reduction exists, what would it mean? If we have an algorithm for F2, then we can also solve F1. But if we know that there's no algorithms for F1, then we cannot solve F2. Now let's take this example as a showcase of a reduction. There are 2 interesting problems I brought for this example. The first one is the independent set problem, where given a graph G and some integer k, you want to find some set of the vertices where the set comprises more or equal than k and no vertices in the set has a line that connects them. Meanwhile, a clique problem has the same input as set but wants to find a k clique or complete subgraph of k vertices, or it could be more. Let's try to construct a reduction from the independent set to the clique problem. We use the same number as from the independent set, but instead for the graph, we take the complement of the graph, which means that we erase the graph from the complete graph that can be constructed from the vertices. Then, the original independent set will transform into a clique for the new graph, since originally there was no edge connecting in the vertices of the set to each other. There are indeed other reductions that are constructed by interesting designs, but let us see just one more reduction in this example and move on to our main discussion. First, there are n Boolean variables, starting from x1 to xn. Each Boolean takes either a true or false value. A literal is either the Boolean itself or the negation of it, and a clause is a disjunction of those literals. We can make a conjunction of those clauses called a CNF. Like this example. Now, we take the set problem Now, 3 CNF means that there are exactly 3 literals per clause. Now, the 3 stat problem would mean that does there exist such a truth assignment where the CNF is true? 3 stat is particularly useful and powerful for these reductions, and one option for constructing reduction is that if you're stuck, then your consideration is 3 set. Now, let's try reduction from 3 set to the independent set problem. We first connect each three literals for each clause to create a triangle, and connect each literal to its negations. We set k to be the number of clauses, and we are done with the reduction, although we need to prove it. If there exists a solution for the three-side problem, we could select one true literal from each triangle, which would make an independent set of size k. On the other hand, if there exists an independent set of size k for the graph, this would mean that the set is constructed by picking each exactly one vertex in each triangle. If we set those literals true and other variables in a consistent way, the truth assignment is consistent and all clauses will be true. Now let's look at why we talked about polynomial time reduction. We say that the algorithm A is polytime if for every string S, AS terminates in most PS steps, where PS is some polynomial and S is the length of S. For example, it might be surprising, but the algorithm that checks if a number is prime is polytime through the AKS algorithm. Given this, let's now define P and NP. There is the definition based on Turing machines, which is quite unintuitive, so I'll introduce a definition that's equivalent but much easier to understand. P is the set of decision problems that can be solved polytime using a DTM or deterministic Turing machine, but for now you can just think of it as a normal Python program. NP does not equal non-polynomial time, but rather non-deterministic polynomial time. This is unintuitive, and an intuitive definition is as follows. We first define an algorithm C as T for a certifier for problem X, where for each string X, if X is equivalent to that, there exists a string such that C as T equals true. Such T is called a certificate, and NP is defined as the set of all decision problems that are solvable using a polytime certifier. For example, let's think about the independent set problem we discussed before. We can check for each vertex pair in the independent set, and to check if they're connected. If they are, then it is not an independent set. Or it is, else. Similarly, the three-side problem is also NP. One thing we can notice easily is that every P problem is NP, since we can set the certifier with the solving algorithm. Another thing is that every NP problem can be solved at least exponentially, since first there exists a polytime certifier for the problem, and we can just check all string T with length until PS. If any of those returns yes, then we return yes. The main question is whether P equals NP. There is a million prize for solving this problem, but why? This means that there exist efficient polytime algorithms for solving TSP, SAT factoring. Especially factoring solved in polytime would break RSA. And would eventually collapse the economy. Thus, the consensus is that P does not equal NP. Now then, Cook and Levin proposed a very interesting theorem which won the Turing Award, called the Cook-Levin theorem, where it states that every problem in NP can be reduced to set. From here, we can now define NP-Completeness, where we state that a problem X in NP is called NP-Complete, if for every problem in NP can be reduced to X. Thus, a simple way to show NP-Completeness is to first choose an appropriate NP-Complete problem and construct a polytime reduction from the problem. But Cook's theorem would mean that since SAT is reducible to any complete problem, and every NP-Complete problem is reducible to SAT, this would mean that if any NP-Completeness problem is reducible to each other. This would mean that if any NP-Complete problem is solvable in polytime, all NP-Complete problems are solved in polytime, and vice versa. Let's sum this up. If X is NP-Complete and solved in polytime, this should mean that the set of NP-Complete problems are inside P. But since P is an NP, this would equal to P equals NP. If this was successful, I would be talking about the topic. Unfortunately, no NP-Completeness currently has a known polytime algorithm. If you look at the effects again, math proofs can be found by computers automatically, which means that creativity can be automated, or factoring polytime can be solved by economically potentially collapsing. That's why most scientists agree on P does not equal NP. A misconception is about NP hard problems, which does not require the problem to be in NP, and NP problems cannot also be in NP. There are already NPR problems that are not NP-complete, such as optimization versions of NP-complete decision problems. Beyond this scope, in many fields, there exist NP-complete problems such as financial engineering, game theory, physics, biology, engineering, politics, statistics, etc. Then should we just give up when we reach such a problem? The answer is no. We should try other problems to at least cover such part of the problem, such as solving subproblems in polytime, or finding approximations and proving they at least find some portion of the optimal solution. Another part of this is that there are also problems in the exponential range, but not NP. And among them there are problems called P-space, which are problems that cannot have a polytime verifier. That's why my question I put beforehand was yes and no. Some problems can be solved easily, but some problem questions remain a mystery.
You can go deep inside these collective fields, which contain great potential for each. Maybe one day you might be a master of these fields and solve the grand old problem, P equals NP, and solve many problems in polytime. It's time to tell.